Okay, what we're looking at today is simply a little bit about how you map out the overall process of solving uniformly accelerated motion problems. So one typical situation is where you're given the acceleration a1 of t, and we're thinking in terms of the context of today's document, and this is 1709. No, it's 11. I might have dated it 12 because I was thinking ahead to tomorrow's classes and had that in my mind. So I might have accidentally dated that 012, but it'll be one of those two dates. Okay, so in the first problem, we're given our acceleration function a1 of t, and we're given v1 at a given time, which I call t sub a, just to distinguish it from other times like t sub b. Clock time t sub a, so we have the velocity at clock time t sub a. We don't have the v of t function. This just means we have, if v1 of t is our function, we know v1 at t sub a. We don't know it at any other time. And we know x1 at t sub b. And now we know that with a1 of t, we can integrate to get v1 of t, since acceleration is a derivative of velocity, velocity will be an antiderivative of acceleration, and use our v1 of ta, which we plug in order to evaluate our integration constant. So then we get our v1 of t function, and we can integrate it to get our x1 of t function and plug in x1 of t sub b to get our integration constant and get our function x1 of t. And this is something we've already done, so we're just drawing a schematic of how all that works together in case this sort of diagram is helpful to you, and in case constructing diagrams of this nature becomes helpful to you in solving problems. It will for many people. It won't for everybody. It just depends on how your brain is wired and what modes of thinking you prefer. But I will want you to at least know how to do this, so it's a tool that you have if and when it becomes useful to you. Okay, then we have a question about the graph of v1 of t. Now, a1 of t was linear, okay? So how do we get our graph of v1 of t? Well, a1 of t is linear, so v1 of t is going to be quadratic. How do we graph a quadratic? Well, we know that the graph is parabolic. We have a negative coefficient of t squared, and that tells us that it opens downward. And we can sketch the graph by finding the axis of symmetry and so forth, graphing by transformations. Okay, that's straightforward enough if you have mastered pre-calculus, and unfortunately most people haven't, so this is a little shaky. But at least finding the axis of symmetry and the vertex of the graph and a couple of other characteristics are really quite easy, and I can illustrate that over here. Okay, so if we have an x2 of t function, and here's the x2 of t function I have. Okay, how do we graph that? We find the axis of symmetry. What's the axis of symmetry? Well, if y equals at squared plus bt plus c, the axis of symmetry is negative b divided by 2a. So we take the b coefficient, which is a coefficient of t, the negative of that, and divide that by 2 times the coefficient of t squared, and we get negative 11 over 18 seconds. And then we approximate that as negative 0.6 seconds. Now, I'm having a rash, and I hope this doesn't continue forever, but I'm having a rash of careless errors. I wrote down the 0.6 seconds because I was busy verifying to myself that 6 times 18 was close to 110. Well, that's very easy. 6 times 10 is 60. 6 times 8 is 48, and 16 48 is 108. Yeah, that's close to 110. So my negative 0.6 works. But of course I didn't say negative 0.6. I was busy getting the 0.6. And in any case, compare that with the fact that 12 over 18 is 2/3 would be 0.67. Yeah, sure, I had 0.6 right, but I neglected to write down the negative, okay? The vertex, in any case, occurs on the axis of symmetry at t equals negative 0.6 seconds, and x of negative 0.6 seconds turns out to be about 16 centimeters, not 24 centimeters, because I calculated the 24 when I had a positive 0.6. And let's verify that. 0.6 squared is about 0.36, and 0.36 times 9 is pretty close to 3. And then we subtract 11 times 0.6, which is 6.6, so we're subtracting something like 3.6 from 20, and we get 16, maybe 17. It might round off to, it's between 16 and 17. So we get this. And I just used 16. So here's the negative 0.6, and here's the 16 for 16 centimeters. And there's our vertex. I made a number of silly errors here. First by plotting at 0.6 instead of negative 0.6 and trying to put the vertex there, and nothing worked, especially since I had the wrong number here. In any case, we have this, and of course our y-intercept, well, it would be the x-intercept in this case. Our vertical intercept occurs when t equals 0, and that's 20 centimeters, so we got the intercept here, and now we know where our parabola goes. Okay, now we'll often, if the parabola passes through the horizontal axis, we get 2 points on that horizontal axis, the zeros, and you just use a quadratic formula to find the zeros, and you can come up with a good plot. In any case, there's the parabola. And then we also talked about how two parabolas can intersect at no point, they can intersect at 1 point, they can intersect at 2 points, or they can intersect at an infinite number of points. Okay, so just a quick sketch. I did this by gesturing in class, and I think everybody understood it. If you got a wide parabola up here and a narrower parabola down below it, well, this narrower parabola is going to catch up with this wider parabola at 2 points. If you have a parabola that's upside down and another parabola that's right side up, well, this one's going to hit this one on its way down, and this one's going to hit this one on its way down. Okay? So it's obvious that there will be 2 points of intersection. There could be no points of intersection. We've got a wide parabola here and a narrower parabola here. Okay? This is going to increase much faster than this one, and they might never meet. Okay? And if the narrower parabola is directly above, if the narrower parabola shares an axis of symmetry with the wider parabola, they can't meet. And these are all things that are fairly easy to prove. So there are other cases, one case being where the parabolas have the same vertex and the same width, if you like, the same value of A. Okay? So that same vertex and the same value of A, the same coefficient of t squared, in other words, they're going to coincide. Okay? And then you'll have infinitely many solutions. They'll be the same parabola. So just a little bit about parabolas, and they're kind of important because if we have linear acceleration, we get a parabolic velocity graph. If we have constant acceleration, we get a parabolic position graph. So parabolas are going to occur, as will straight lines, fairly often in our analysis of motion.